Thank you. Hopefully you can hear me at the back. So what I'm going to talk to you today about the challenge that London faces and trying to understand what short-lived events are. So just a quick introduction. So I'm an operational modelling and visualisation manager. I've worked in TfL now for 13 years. I'm a trained civil engineer. And one of the big tasks that I have to do is basically ensure that schemes that are put onto TfL's network are fit for purpose, provide benefits and balance all needs. So just to understand, I think it's important to understand the challenge that TfL and London is. It's a growing city, 9 residents every hour, a car load every 26 minutes, 2 bus loads every day, 2 tube trains every week, and projected to be 10 million population by 2030. So that's quite significant. Included in that is obviously with that population growth, as you can see, quite spread across the network, with quite significant employment. Particularly East London is a growing area, and obviously now we've heard about Heathrow and the potential for Heathrow. I'd expect in more increased employment on that. So what does that have an impact on the network? Well, that means 3 times growth in cyclists, a 30% increase in bus travel, extra vehicle kilometres, additional freight to service all those offices and people. And as you can see, it costs £5 billion a year to London's road network, and 15% of traffic congestion in the UK is in London on that 1,500 kilometres, which is just unbelievable. So to try and understand this, we need the tools that we have available to us. We have traffic models. So just to give you an understanding, what is a traffic model? Well, it's really a simplification of the real world. Enables us to emulate the movements of goods, cyclists, pedestrians, buses, taxis through London's road network. And using that knowledge, we try to replicate models that represent what the traffic network looks like. That's quite a task in itself. That takes several days and months to achieve that. But from that, we can then start to test scenarios and do predictions. And those predictions we can then add value to that. That could maybe support a business case for a new development. So why do we need them? Well, I would argue that they're probably the only tool that we do have available to us. So we can understand the impacts on the street. We can do any work in an offline environment. So we don't have to go out and test, put some barriers on the road network and say, okay, we're going to now apply a new bus lane here. As you can imagine, we're increasing that congestion and that cost to the economy. Plus, we can also test contingency situations. So one of the things we did during the Olympics was to try and understand how can we get the VIPs from the different venues, but without actually impacting on the general traffic. That's quite a challenge to do that. But we can do that in a model, and the model can give us a good prediction. So what we're doing, as I said, we're trying to balance the needs of all road users, and by doing that we can help predict what the impact is. Plus it's a tool we can then use to communicate to the public. The public don't necessarily are sceptical, I would argue, about models because they feel it's a black box, and a black box just spits out numbers, and we just interpret those numbers in a particular way. One of the tools we use now is visualizations. You can see a number of visualizations that we use to give the public an understanding of this is how it look and feel like, even though there is algorithms and data behind it. And again, from that we can then maximise the benefit of the scheme in the long term. So today what we're going to kind of talk to you about is that short-term horizon. So what is that horizon? How long are these events, do they last for, and why is it important to quantify? So we're talking more about a 1 day, 5 days or 30-day event. They're quite common on London's road network. They are predominantly emergency roadworks or they're planned closures. And understanding and quantifying them is important because we are costing the London economy, and 20% of these activities contribute to that cost. So if we take our traditional kind of transport modelling, so a traditional transport model, we would say, okay, we understand people have an activity they want to take, so we get that information from postcode surveys, or we take census data. From the activity, then that individual has a destination to go to, so in this particular instance they're going to a cafe. They will take a particular mode that they want to take, and then there's the route that they would choose. And the route is based on what we call value of time. It's the cheapest route possible for that individual. So again, the traditional model, we use a static traffic assignment algorithm structure. So you have a link cost base on its link flow, tries to find what's called the shortest path, and then it updates that with the link flow. Now it does that in a cycle, and that usually takes several hours to do depending on the size and the complexity of the model. Once it's reached its convergence, these are the kind of things. So it's saying that the pass and the travel time are equal, then it should stop, and that the flow changing then should stop. The issue we have with that is, unfortunately, it gives a uniform profile. Now that's not reality, really. So that's one of the challenges that we're obviously trying to tackle. So I'm just going to run a quick model for you to try and kind of give you an indication of what I'm talking about. So this is our transport model that we have, and we're going to look at
Visualizations show the western portion of inner London around Parliament Square. The simulations are based on outputs from vision modelling completed by Outcomes Delivery's modelling and visualizations team. Each dot represents a vehicle. Blue is a mix of general traffic, cyclists are yellow, whereas red are for buses. The size of the dot represents delay. The larger the dot, the more delay being experienced. The base situation is pre-road modernisation plan build with no active traffic management applied. Note, it is fairly free-flowing, gyratories are working well, and buses are not generally delayed. The second situation shows work typical of the road modernisation plan, in this case for the east-west cycle superhighway on Victoria Embankment, without any active traffic management applied. Already we can see the dots are getting larger, equaling more delay, especially notice on buses. Queues are in general longer. Gyratories at Parliament Square, Trafalgar Square and Hyde Park Corner are locking or in danger of locking. Eventually there are queues on Whitehall, Victoria Embankment, even over Westminster Bridge. All of this emanating from a fairly small set of works. Finally, we see the same situation with active traffic management applied, by limiting traffic into the network at a manageable level for the size of work using our active traffic management points. Delay is noticeably down on the no active traffic management situation. Queues are shorter, gyratories are kept moving, and buses suffer less delay. By implementing this London-wide strategy, Transport for London's Outcomes Delivery team were able to maintain journey time reliability and protect bus.
Right. So what that's doing is that's effectively, because that's using that static algorithm, we still have the same uniform flow of traffic coming in, and all we're doing is managing those points on the network. The reality of this is that traffic will divert away from these from this area, which is what we're going to talk about. So again, what we're exploring and what we're interested in is this dynamic traffic assignment. So what it's doing, again, it's understanding and simulating it at the time it will take to travel by the link. It's still, again, trying to find the shortest path, but it's using vehicle path assignment. And when it comes through doing its convergence, again, the slight difference now is that it's using the stop flow to change, which then we then create a more dynamic flow link, which is more what reality is. So in a sense, just to summarise, so the static's giving us a fairly uniform demand. The network capacity is uniform. It's loading arrivals at destination of all trips, and junctions can be permanently at capacity or under capacity. Whereas dynamic gives us more, not an ununiform demand over the study period. The network capacity is not uniform as well. Again, that's because it's fluctuating all the time. Time it takes for trips to complete the journey are not uniform, and different junctions become at capacity for different lengths of time and for different periods, which again is kind of more what reality is. So that's realistic behaviour. So for the last 3 years now, we've been kind of trying to understand this problem and how we go about tackling it. So the first thing we've been doing is trying to understand data. What kind of data can we actually use? So we've explored Bluetooth. We've done a number of Bluetooth trials on the network. Again, Bluetooth gives us a great sample. Only issue with Bluetooth is that not everyone has that on their phone. Some haulage companies actually have Bluetooth in their cab, so again we can identify the type of vehicle that's being used. That proved a success. Downside of it is that you have to install detectors on the network, and several of them try and give you the capture rate that you're interested in. We also explored Twitter. So TfL has 700,000 Twitter followers, and again trying to use keywords like the previous gentleman before lunch was talking about, was using keywords in Twitter to try and simulate and understand incidences on the network. We then also explored using mobile phone data. So everyone carries a mobile phone with them. Are we able to track those movements across the network? Again, we could do that, but one of the issues we had was trying to disaggregate the trips. Is somebody on a bike? Are somebody in a bus? Are they in a car or a taxi? So it was quite difficult. But also as well, probably the one which we felt was most promising was moving towards GPS data. So TomTom was a great example of something that we could use to try and understand trips around the network. So the second part of it was then we worked with MIT and a company called TSS Aimson to try and understand that dynamic assignment algorithm. So basically we're trying to look at more mid-term responses, and again that was fairly successful in understanding the algorithm, but the key part of this was data. So as we were trying to understand this solution, we were trying to work out really what the steps we needed to take, and so origin destination data for us was key. We needed a study area that was something that happened in the past, so we picked Kingsway Fire. We've obviously got a dynamic assignment algorithm now that we could test, plus we've got traffic modelling data from which we can then use. So we obviously did a number of kind of tests using Google Journey Time to work out where were the key journeys when the fire happened and what traffic was moving around that short-term event. We then used the test different versions of the software to try and then determine how effective that algorithm was. Was it predicting the right sample of movements in the network? Could it then be used as a proper forecasting for that short-term horizon? And then explored really different versions of the other case studies in terms of road closures as well. And then use CCTV again to try and validate the outcome. So just with the TomTom data, we did a number of queries on this. TomTom's got history of up to 2 years. Downside of TomTom is that again it's not a great sample. Not everyone has a TomTom unit in their car. So we explored using TomTom to give us that sample. Unfortunately, the sample only worked out to be about 5%, so again, it wasn't successful for us. And we then went pretty much back to the drawing board to try and understand what other data we could explore, and that's currently where we are at the moment. So just in kind of conclusion, where we are today with this is that, again, we've had limited success, partly of the issues with tracking data, understanding that origin destination data. We're exploring some other test cases, so we now have currently Tower Bridge closure, again trying to use real-time data to try and give us that prediction. But also we're looking at machine learning, whether we can use machine learning tools using real data to try and again give a prediction. So that's basically where we are. Just before I conclude, I just wanted to kind of show you a video that where TfL is going with its data and technology.
We are Transport for London. Our purpose is to keep London moving, working and growing, and to make life in our city better. London is booming. Our population is growing and set to reach 10 million by 2030. We must keep pace with this growth, providing a transport system fit for one of the world's greatest cities. To do this, we harness technology and data to extract every ounce of transport capacity. The byproduct of all this technology is intelligence. We use it to deliver excellent customer services and improvements to the system, while driving costs down. We gather raw data from a number of touchpoints, including our vehicles, traffic, counters, websites and ticket systems. We then transform this data into products and use it to inform our service planning and share the information back with our customers. This intelligence keeps our system running smoothly on a daily basis. By analysing data, we can detect patterns or trends by dealing with the problems as or before they even occur. This means we can notify passengers via tailored alerts on the network and refund our customers when things go wrong. This means that we can prepare for increased travel demand during events. We can plan for disruptions caused by major roadworks and track maintenance to make the network more reliable and give our staff on the front line better, more accurate tools to help them improve their customer care. We can now tell where customers are leaving the bus using an algorithm that combines bus location and ticketing data. ODX, Origin Destination Interchange, is used to build complete journeys on our network. Even with a project as extensive as the Cycle 2 behind us, using analytics meant we could build immersive 3D simulations which brought life to the best possible solution, making cycling in London safer and more accessible for all. So where do we go from here? We won't be working alone. As champions of open data feeds, we have enabled even better real-time customer information with hundreds of third-party apps built by a growing independent development community. We have never stood still when it comes to technological improvement. Our challenge now is to anticipate the new technologies and innovations that will change how we travel. One thing is certain, big data will be a key player in the shaping of the life of our city over the next few decades. And effective analysis and application will help us to make better decisions for the benefit of all Londoners.
Thank you.
All right.
Yeah.
And again, we have some time for questions, so let me open it up to the floor. Yes, please.
You talked about a lot of different data sets there, and I mean, for example, for GPS,
Yeah.
the uncertainty associated with it is variable over geography. For Bluetooth, you mentioned there's bias associated with it because no one has it.
Yeah.
Something similar with mobile phone data, no doubt. Have you done any work about pooling those, trying to understand how that uncertainty might propagate through?
So one of the things we're kind of exploring is, potential data fusion. So if you've got different sources of data, could that data be fused together to give you the full picture? And that's something we're trying to explore. because we know, I don't think we'll ever get a full data set that solves the problem that we're trying to solve here. But we may be able to get good rich sources of data that could be supplemented against maybe something that's not so good, to give you kind of to fill those gaps in. But again, that's a massive challenge, and if anyone here has got the solution to it, I'm always interested to hear. Yeah. Yes.
In the back?
Can you use Google Map data? I was thinking about the Chinese research, Baidu, I think it's called, I don't remember exactly the name. They used the data that were collecting because of people searching for their route in order to develop an algorithm.
Yeah, I mean, we did have a number of conversations with Google, because Google, if you have an Android phone, Google is actually tracking you, I believe. I don't know if you know that, but yeah, Google's tracking you. Yeah. And but the problem is there's then a cost to that. So if you imagine the kind of information that TfL is interested in, that population, the cost potentially of getting hold of that data could be huge. But yes, it is a potential source, but can it be weighed up against the cost of it?
Good question.
So you've got two main functions of TfL. One is the long-term strategic traffic planning, and others are short-term. I mean, as a Londoner who lives in London, speaking frequently to taxi drivers, if they think you're stuck with a lot of legacy projects in all these bike lanes from the previous mayor. I mean, some of your strategic things are really political. I mean, it's a very difficult environment to work in, isn't it? I mean,
it is.
Long-term stuff.
Yeah, I mean, obviously we have a change of mayor potentially every 4 years or for 8 years. He or she will have their own transport policies, but TfL is there to serve the London commuter and the London population, and all we're doing is implementing policies that mayor has. And I think long-term strategically we are good at an understanding. So, for instance, the Olympic Games and all the work that was involved in getting that to work, that was done, yes, over several years, but understanding kind of that more short term when things go wrong, how quickly we can react, but how quickly can we predict that? I find that we're kind of lacking in that kind of knowledge and expertise and technology. And as I said, if that 5 billion a year cost in congestion, and 20% of that is caused by roadworks, if we could then develop something that can give us a better prediction of the impacts of that 20%, we could start to mitigate, and that's saving TfL and saving the London economy, a lot of money. So.
More questions? Yes, go ahead.
Your transport models must be quite big and complicated and have lots of parameters in them. So how do you go about validating those models?
It's a good thing we got 5 minutes.
Well, we invest a lot of money, so things like census data. We've now stopped doing what's called roadside interviews. We used to do those because they're now about £20,000 per survey spot now, and obviously then again the cost of the delay. We obviously do postcode surveys. We've got lots of other data that we're using, so we understand the bus routes. And on average, depending on the size, we've just finished a pan-London model now. That took us roughly about 18 months to do, with about a team of about 15 people. Again, the model's only as good as the data that we've got. And we spend probably about £1 million, probably more, but roughly about £1 million just in data itself, let alone the time and for people to then develop these models. So it's a constant challenge. I think TfL is in a slightly fortunate position where it's now starting to, as the video is showing there, that more open data. So a lot of data is now freely available, and we're encouraging more people who've got expertise in using that data to try and help us develop tools, particularly the origin destination for the buses. That was done by an independent developer, basically just using our Oyster data. Again, it's a tool that we can use, and then that tool can then benefit our customers. But yes, it's a massive challenge, and I'd like to think in the future, when data becomes probably more readily available and more of a quality, more rich in its form, that we can then start to make these things a lot shorter and more efficient. Does that answer your question?
Do you have ways to try to tinker with the traffic, for example? Can you, for example, change traffic lights to try to reduce queues in a kind of a live system rather than...
Yes, so we do have that. So so Transport for London manages 6,500 signals, traffic signals in London, and roughly about 4,500 work on what's called a dynamic real-time system. So we have loops that slot into the road that's counting cars, and that system feeds all that data, and it's then adjusting the signals in real time. So we have that system there, and that's been fairly established for the last 20 years. But again, it has its limitations. We're not able to disaggregate different modes. So it's basically just treats every car or vehicle that passes over that as a unit, and so you can't distinguish between what type of mode that is. But it's efficient and it works, and it's
I've got time for one more question. Any last questions for Marcel? Okay, in that case, let's thank Marcel again.